So hello everyone, this is our seventh tutorial. Today we will discuss connectedness. Recall that a topological space X is said to be connected if you cannot break the space X into two disjoint open set. X cannot be written as two disjoint open set. If you can write X as two disjoint open set, then X is not connected. Here, sorry. Can you hear me? Hello. Hello. Can you hear me? Kawaljeet? Voice is not coming. Okay, let me rejoin. Can you hear me? Hello? Hello? Kamalji, is it audible? Hello? Hello? Hello?
Yes, sir, now audible.
Okay, okay, thank you. So X is said to be connected if this is not true. That is, X can be written as disjoint union of two open set. U here, uh, U comma V, those are non-empty and not equal to R, not equal to X. If this is not true, X is connected, that means if you try to write X as union of two open set, disjoint union of two open set, that will imply either U is empty or V is empty. U here open sets, disjoint open set. Okay, connected means this property. Connected imply this, and if uh, this is not satisfied by X, then X is said to be disconnected or not connected. Okay, and some important properties are like this. So suppose A is a subspace of X, then if A is connected, if A is connected, then if you include, if a limit point of A is included, then that is A union some limit point. Limit point included means A union some limit point. Some limit point. Then the new set, this set is, then it remain connected. Okay, the property says if you choose a set in between its closure A and a closure of A, so this is same as saying if B contain in closure of A and B also contains A, then if we assume in this case if A is connected, then B is also connected. Okay, this is equivalent statement. Equivalent. So in particular, we also get a closure. In particular, closure of A is always connected. So in between a connected set and its closure, all the sets are connected. Whatever set you choose in between a connected set and its closure, all those sets will remain connected. We have already seen this set open 0 1 union 2 3. This is disconnected, right? Some example. Those are disconnected because this set is written as disjoint union of two open set, right? But we also know that R or any interval is connected. So R can also be thought as interval because R can be written as minus infinity, comma infinity, open interval. Note that R can be written as minus infinity, comma infinity. Even a singleton set can be written as closed A, comma closed A, right? So sometimes this may not be allowed, but this is some notation. So interval is always connected. Take any interval of real number. This is connected with respect to usual topology. And more than this is true, that is, the only connected set of real number is interval. Okay, so a set which is a connected set of real number. So if I don't mention a topology, then always assume it is usual topology or Euclidean topology. So a connected set of R is interval. Is an interval. Is an interval. So, another important property. Suppose f maps x to y is continuous map and x is connected. If we assume those two things, then f of x, which is a subset of y, is always is connected, right? So in particular, quotient phase x modulo some relation is always connected. Why this is true? Because we can thought x modulo some relation as a cosine map, x to x mod some relation. This is a cosine map, and we know cosine map is always continuous map. Cosine map is surjective, so image of this Q is whole x modulus that relation, this cosine phase, right? So continuous image under continuous map, image of a connected set under a continuous map is always connected. So we assume that space, if x is connected, then x modulo that relation is connected. So we already assume that x is connected. If x is connected, then x modulo this relation will also be connected. But what about subspace? We have already seen that this is a subspace of real number, right? But this, though real number is connected, this is not connected. So as a corollary, if we assume those two theorem, two lemma or two theorem, then as a corollary, we get the following property: intermediate value theorem or intermediate value property. Value property. So this property says if F maps X to R, R with usual topology and X is equipped with any kind of topology. If this is continuous, and X is connected, let A Fx less than some real number less than y, or if let us consider let x1 x2 belongs to x, and and choose a real number between fx1 and fx2, then the theorem says there exists some x such that there exists some x belongs to x such that f of x equal to r. So take any real number between those fx1, any intermediate value between this fx1 and fx2, there is always some element from the domain whose image is that intermediate value. This is the intermediate value property. You can see this this can be derived from the above two property, that is image of connected set under a continuous map is connected. So if you see this property, then we have assumed x is connected. So f of x, this image set will be connected in R, right? But we also know that connected set of real number always be an interval, right? So interval means if something belongs to this fx1 and fx2, sorry, uh, yes. So fx1 and fx2, those 2 points belongs to image, right? Fx1 and fx2, those 2 points belongs to this f of x, this image set. And this image set is also interval. Interval means if you take any point between this fx1 and fx2, there are some x whose image will be that set. So image set interval means any point between this fx1 and fx2, all those points are already contained in fx, right? So this is how we can see this property, but it is actually, you can derive it independently. This is very important property. So those are the important facts about connectedness. And there is another definition. Connected component. Right? Component means, so connected components, suppose x belongs to x be a topological space, then the connected component which contains x, it will be defined by taking all connected subset, take all connected, so let me denote it by cx, connected component which contains x. Connected component containing x, it will be defined by union of connected set, connected subset containing this x. Okay, so this is how you can define connected component. And the interesting thing is that this relation x related to y, if and only if x comma y belongs to same component, it is equivalence relation. This is easy to see, right? X y belongs to same cx. This is an equivalence relation. That means the topological space x can be broken into its connected components, right? So those forms a partition of the topological space x. So x can be written as disjoint union of those connected components. Okay. And another interesting property is that this connected component Cx, it is always a closed subset. Why is it closed? Because you can see the closure of Cx is always containing, always contains this Cx. But on the other way, uh, if you we already know that if a set is connected, then its closure will also be a connected set, right? So Cx is the maximal connected set. Therefore, Cx bar must be same as Cx. Other, if though there is some inequality, then this Cx bar will be strictly bigger, which is a contradiction. So this is not possible. Therefore, Cx, connected component Cx, is always same as closure of Cx. That is, connected component is always a closed set. So those are some interesting properties. So let us solve some problem. So first problem says, which of the following are connected? So tau I are topology on the set X which equal to A comma B comma C. Now what about the first set, first topology? So I want to say which following are connected means which of the following set are connected. Okay, so x with respect to this tau 1, x with respect to, so is what about the first one, is it connected? You can see the space x can be written as disjoint union of open set. If we consider tau 1, x can be written as disjoint union of open set. Those are open. Disjoint. So this is disjoint union of open sets. Therefore, from here it is clear that x comma this tau 1 is not connected space or disconnected. Now, what about x with respect to the topology tau 2? Can you write x as union of two disjoint open set? So, in the second case, you cannot write. So, x has three elements a, b, c. But it is clear from this topology, you cannot write, you cannot break this space into two disjoint open set. For example, if you choose A, there is no some B or C. If you choose AB, there is no open set C. So you cannot break X into two disjoint open set. Therefore, this is connected. With respect to tau 3, you see that if it is connected or not. So uh, for C, there is a non-trivial partition. Not partition, X can be written as union of two open set. But the thing is that those two are not disjoint. Not disjoint. Hence, it is again not. It is again connected. Okay, X cannot be written as disjoint union of two open set. Therefore, X is connected. And D is indiscrete topology. D is also clear. There is no non-trivial partition. The only possible partition is empty union X. Only possible union, this expression is empty union X. But though those are disjoint, right? Their intersection is empty, but this union should be non-trivial. Means empty union X, this is not allowed. Okay. So you need to write, you need to break X into two non-trivial disjoint union. So non-trivial is also important. Non-trivial disjoint union. So the only connected set, only so all those are connected, right? This is connected, you cannot break. This is also connected. This is also connected. You cannot break X into two disjoint non-trivial open sets. Now, which of the following are connected? Same question. Can you see that R comma cofinite topology, is it connected or not? What is the answer? So let us try to write. So note that cofinite topology, what are the open set in cofinite topology? So open set means it is a complement. So we are considering cofinite topology. Cofinite for the option A. So open set means complement of some finite set, right? Now can you see that R cannot be written as union of two such sets. So if we try to write R as, there are two possibility. Another possibility will be uh, empty set. Empty set is also open. So open sets are either complement of some finite set or empty set. So if we try to write R as union of disjoint union of uh, U and V, then what is the problem? This means take the complement. Empty can be written as U complement union intersection V complement. So complement of some finite set. So U and V are complement of some finite set. That means this is finite. Complement of U is finite. Complement of V is also finite. But intersection of two finite set. Sorry. Do we get any contradiction? R, R is written as disjoint union of R equal to U and U union V. It is possible that U complement intersection V complement. Oh, we also assume. So let, if possible, let such a partition exist, right? So R can be written as disjoint union. So we are also assuming R equal to U union V, and their intersection is empty. Then what is the contradiction? U complement. Sorry, this is empty. Disjoint union R. If we try to write R as disjoint union of U comma V, are we getting some kind of contradiction? Yes. Yes, Isika, tell me. What is the contradiction are you getting? Hello? Are you saying something, Isika? Okay. Okay, let us try other options. So, for example, what will happen for discrete topology? So if we assume R with discrete topology, then R can be broken into two open set, right? To disjoint open set. Take minus infinity, comma 0, and take close 0, comma infinity. So in discrete topology, any subset is open, right? So this is open, this is also open, and this is non-trivial disjoint union of non-trivial open subset. So it is clear that R is not connected. So this is not connected. R can be broken into two disjoint open open set. Even this is true for any space X. For any arbitrary space, X can be always written as take some x0 and remove that point. X can be broken into two parts. This and this. Both are open and both are disjoint. So provided X has more than two elements. Otherwise, this will be empty, right? If X has only one element. So B is not connected. What about C? Can you see this is connected or not? we are considering topology where the open sets are this kind of ray. Open sets are some a to infinity, this kind of ray. So can you see that if you choose any two open set, it will, it must, those two open set must overlap. Is it? It is easy to see, right? Say, take any open set A infinity and another open set B infinity. Those will always overlap, right? So C, for C, R cannot be broken into two disjoint open sets. Okay. So the interesting thing is that A comma infinity and B comma infinity, any two non-trivial open set, it is some C comma infinity, where C equal to uh, maximum of A comma B. Therefore, it is clear that R can't be written as some U, this is U and this is V. So R cannot be written as U union V. Okay, some U union V. It is not possible where U, V are disjoint. So this is not possible. The only possible is the trivial one, the empty union R. This is the only possibility. So it is clear that R with respect to this topology, this is connected. R is connected with respect to the topology tau. Now, what about R with lower limit topology? So this is connected set because any two open set will overlap. So you cannot break R into two disjoint open set. So what about R with lower limit topology? Recall that lower limit topology on R, this is generated by this kind of element, generated by this basis, right? Where B is some closed A, comma open B. This is the limit point. A comma B are real numbers. So note that R can be written as minus infinity comma 0 union close 0 comma infinity. Okay. So this is open in usual topology. Therefore, this will be also open in lower limit topology. Lower limit topology is finer. So if something is open in usual topology, it must be open in lower limit topology. And you also directly check if something is open or not by basis, right? Because take any point x belongs to minus infinity comma 0, x always lies in this kind of thing. X comma, take something which is strictly smaller than 0, x comma minus epsilon, right? This already contained in this set, this minus infinity comma 0. So minus infinity comma 0 is open because if we take any point from this minus infinity comma 0, there exists a basis element which contains that point, and this basis element contained in this minus infinity comma 0. By the same check, we can see that this set is also open because the left side is open, which is similar to this one. So this is also open in lower limit topology. And the interesting thing is that if we assume this as U and this as V, then U intersection V is empty. And also note that both are non-empty. U is non-empty, V is non-empty, and their intersection. So R can be broken into disjoint union of non-trivial open sets. Therefore, R is disconnected with respect to this lower limit topology. Lower limit topology. So this is disconnected. Now let us see what happens in cofinite topology. Uh, so okay, let me write in a different way. So this is empty. So we are assuming U comma V, those two are open set. Okay, open, non-empty open set. U V are non-trivial open set. Non-empty open sets. Then U can be written as complement of A, and V can be written as complement of B, where both A comma V are finite. Those are finite set. Okay. Now what happens? So U union V, this is A complement union union B complement, which can be written as, sorry, let us see U intersection B. So this is A complement intersection B complement, which is A union B whole complement. Right? Now, so A and B are finite set. Therefore, this is finite set. Union of two finite set is finite. So, if we take the complement, then this cannot be empty. Right? So, therefore, there is no such partition. You cannot write R as a disjoint union of two open set, non-trivial open set. That is, the problem is any two open set in this cofinite topology always intersect. Take any two open set, it must intersect because it contains almost every point except some finite point. It has all the points. Similarly, except some finite point, B has all the points. Therefore, this must happen, right? They must intersect. This is the proof that because union of some finite set is finite. Therefore, so any two non-trivial set always intersect. The same problem happens in this case. Any two open set intersects. Okay. Therefore, it is clear cofinite topology with respect to cofinite topology. This is connected. You cannot break R. R cannot be written as U disjoint V. If we assume this condition, those are non-empty set. You cannot write R as disjoint union of U comma V. Disjoint union, because any two non-trivial open set must intersect. Okay, so this is the problem. Therefore, it is not connected. Now let us see if the following is true or not. So the set K is 1 by n, where n is natural number. So we are seeing, we need to show that this set is connected or not in the in R2. So we are considering R2. Okay. So let us draw the picture of R2. So this is R2, right? X-axis and Y-axis. Now K cross 0, 1. K cross 0, 1 means K is 1 by n. N varies over natural number. So let us try to draw. So it is 1 half and 1/3, 1/4 like this. Okay, 1/3, 1/4, and it will approach to 0, some 1 by n. So K cross 0, 1, that means those are some vertical lines, something like this. This is 1 half and similarly like this. Okay, so this is for example, this is 1 cross 0, 1, and this is half cross 0, 1. So this is our K cross 0, 1. Now let us try to draw close to 0, 1 cross 0. That is same as this x. It will lies on this x-axis. Okay, this is 0 comma 1. This interval on the x-axis. Now 0 cross 1. This is 0 and this is 1. So 0 cross 1 means this point. It is represented by this point. Okay, this is 0 cross 1. So now the question is it connected or not? So the statement is this set is connected. Is it true? So I have not drawn the space completely, but there will be some smaller lines. So it will look like a comb. This space is also known as comb space because it looks like a comb. So just see that this is our one. This is also included. This and this. Then those points will become more dense here, right? And it will approach to 0, but it is the points on the y-axis will be not there. So what is your answer? Is it connected? Let us try to see. So if we remove this point, will it be connected? K cross 0, 1 union of close 0, 1 cross 0. So now it is easy to see that this space is same as this with this kind of thing. It will become dense. So is easy to see that this space is connected. So this space will be connected. Why? Because we know that if A and B are two connected set, if A comma B are connected and A intersection B is non-empty, there exists some point which belongs to both A and B, then union A union B is always connected. Okay. So note that union of connected set may not be connected. For example, take this open 0 1. This is a connected set in R2, and take 1 comma 2. This is also connected, but their union is not connected. So the condition is this. So if their intersection is not non-empty, then this becomes a connected set. Okay. So you can see this set can be written as this. First, let us see inductively. So this set is connected as this is interval, and this set is also connected. This is also a homeomorphic to interval. This is also a closed interval, right? So since their intersection is non-empty, this become connected. So now consider x equal to this and y equal to this space. So again, x and y intersect at this point. Therefore, their union will be connected. X and y both are connected. They have non-empty intersection. Therefore, their union is connected. And inductively, this will hold for all those pieces, right? Therefore, it is clear this is connected. We are using this property. So this property does not only hold for this finite case. If you uh, if you write this for infinite case a1, a2, etc., then the same property will hold. Okay, provided they have some non-empty intersection. So any pair, uh, some pair has non-empty intersection. That is two consecutive pair. If two consecutive pair a1, a2, this has non-empty intersection a2, a3, those two has non-empty intersection like this, then the same conclusion will follow. That is union of ai. This will be connected. Okay, this is just use this fact. You can easily prove that one. Uh, the same proof will work. Actually. So up to this, there is no problem. The only problem is that extra point. So if you consider only these pieces, then it is clear that this piece, this one should be in a different component, right? This cannot be connected with this these lines. It is clear. But the thing is that there are lots of branches. There are lots of lines like this. So this density will create the problem. So if only finitely many pieces are allowed, only finitely many vertical lines are allowed, then it is clear this is not connected. Right? You can write this as union of two open sets. So take an open ball around this and take another open ball around this. You can always write this for finite case. You can always write this as disjoint union of this open ball intersection, this finitely many thing union with this. So this this singleton point and all those things are open in the subspace. If you only consider finite case, so if n is allowed to vary from 1 to some k, then this becomes disconnected. But here it will be connected. Why? So consider the case. So a equal to this. Then note that this 0 cross 1, this point, or or we alternatively write 0 comma 1, this point, this belongs to closure of a, right? So take any open ball around this 0 1, it always intersect. There are some lines which will get intersected by this open ball. This is the open ball around this point 0, 1. Therefore 0, 1, this belongs to closure of A. From geometry it is clear, right? So this point belongs to closure of A. Therefore the property which says if you include some limit points, then the set remain connected. So A union this singleton point 0, 1 is connected. But this is same as this set, right? So this can be equivalently written as 0, 1. Okay. Now what about this question? Here again we are considering some subset of R2 and we need to see if this subset is connected or not. So let us see. So here the graph is x comma sine 1 by x. So for example at value 1 by 2 pi, 1 by 2 pi, x equal to, when x equal to 1 by 2 pi sine 1 over x, this becomes 0, right? Sine 2 pi equal to 0. And similarly sine at 1 by pi, 1 by k pi, this will be 0. 1 by 2 pi, 1 by 3 pi, 1 by 4 pi, like this. And now it will become more dense. So let me draw in a better way. So sine 1 by x 0 if x equal to some 1 by k pi. So this is x-axis. At this point it is 0. Suppose this is 1 by pi. Then at 1 by 2 pi this is 0. 1 by 3 pi. So the curve will be like this. Its frequency will increase. Okay. So it will become denser here. The same space like situation. So this curve is there. Now the question is it connected? If we don't consider this origin, then is it connected? Will it be connected, this zigzag like thing? So we already know that image of a connected set is connected, right? So this graph this can be thought as x comma uh, that is f maps 0, 1 to R2, where f of x equal to x comma sine 1 by x. So this is connected, right? Because any interval in real number in R is always connected. So since this is connected, here the set, let me denote this as S. Therefore S is connected. Why this S is connected? Because S is actually image of this 0, 1 under the continuous function f. So image of continuous function, image of a connected set under a continuous function is always connected. Okay, therefore S is connected. Now if 0 0, this origin is also included, then what will be the conclusion? Will it remain connected or not? Again the same situation will arise. If we consider the origin, then it is clear that whatever neighborhood we choose, this always intersects this graph, right? This will always intersect. There are some branches, there are some curves which will be included in this open neighborhood, open ball, right? So for example, take this interval be this origin comma some epsilon. Consider this, or some 1 by n, a neighborhood like this. Then corresponding to this neighborhood, the point, consider 1 by n pi comma sine 1 by n pi. So sine 1 by n pi is 0, right? This is 0. This always belongs to this neighborhood, because 1 by n pi 1 by n pi is strictly less than 1 by n. Because of this always belongs to b0 1 by n. So there are some points of the graph, this graph, that is uh, graph of this function. There are some points on the graph of this function which belongs to this interval, whatever interval you choose, whatever neighborhood of origin you choose. Okay, this is O means origin. So whatever neighborhood be O comma 1 by n you choose, there are some points on the graph which belongs to this neighborhood, right? So therefore this point origin, which is equal to 0 comma 0, this origin belongs to closure of S. Origin is a limit point, right? This will imply S union this. Yes, go ahead. Any question? Yeah.
Sir, we call it a sine curve.
Exactly. It is called so sine x is sine curve, and it is called topology sine curve. Okay.
Okay, okay.
Okay. Because it is used for some non-example and for a counter example in a topology, which will be seen later. This curve will be used. Okay. Topology sine curve. Good question. So this curve is known as topologist sine curve. So again, by the previous property, S union origin, S union this 0 comma 0 is connected. If you include some limit point, connectedness remain preserved. So up to this, is there any question? Okay. If not, let us see the next question. Here we are considering a topology on R. It is defined by the following. So U belongs to tau, means a set is said to be open. U belongs to tau means the set is said to be open if 0 belongs to U. So open sets are, in this topology, open sets are given by take any set which contains 0. Okay. So alternatively, we can say open sets are a set which contains origin 0. So this is not completely true because empty will also be there. So just so you just include a condition. All non-empty open sets satisfy this condition. So open sets are some sets which contain 0. So this is non-trivial open set. Okay. This is how the topology is defined. So tau contains all those any subset of real number which contains 0. If 0 belongs to that subset, then that will be open set. If 0 does not belongs to that set, that is not open, except empty. Empty is always open. Is it clear how this topology is defined? Tau is U such that U contains 0. And there is another possibility, empty. So this is the topology. Now we need to see the number of connected component of R with respect to this topology. So first let us see if tau is connected or not. Can you see that? Can you see anything if tau is connected or not? So if U comma V, those are non-empty set, then by definition it is clear exactly particular point topology. Yes. So UV, if we assume UV are non-empty set, then 0 belongs to U and 0 also belongs to V, right? Therefore, U intersection V is always non-empty. So it is clear that R cannot be written as U union V. So you cannot write R as union of some non-empty sets because both contain 0. Whatever U and V you choose, both will contain 0. So R cannot be written as disjoint unions. Okay. Disjoint union. This is true if we don't if we don't allow this condition. If this condition is excluded, then this will be true. R can be written as anything. R can be written as 0 union something like this, 0 comma. So R can be written as 0 union something. Take so 0 comma 1 union something R minus 1. So those are non-trivial union of unions which gives R. But the problem is those two are not disjoint. This problem will arise. Okay. So you cannot write R as disjoint union of U comma V because U and V, if any non-trivial U and V will always intersect. So the conclusion is therefore R is connected. So R is connected means it has only one component. Okay, so it has only one component. Yes. What is your question?
Sir, in the previous question, we are talking about open sets which contain zero. Can
Yes.
we talk any real number instead of zero? Not particularly zero.
Yes.
What will be behavior
Yes.
that time?
Again the same conclusion will be true, right? Again we'll get the same conclusion because instead of zero, if we choose some real number p, then the same will u intersection v will get non empty, right?
Okay, sir.
Because p belongs to u and p belongs to that.
Okay, sir. Okay.
Great. So let us see the next question. So here f is a map from f is a continuous map from x to x. The condition that implies f must have a fixed point. So for which condition f must have a fixed point? So do you know what is fixed point? F is a function from x to x. A fixed point x0 belongs to x for this function is defined by sorry, if a point x0 belongs to x is said to be fixed point if uh, yes, is there any doubt? Okay, so a point in the domain is said to be a fixed point if f of x0 equal to x0. Okay, if this is satisfied by a point x0, then that x0 is said to be a fixed point. Okay, now which condition will imply f has a fixed point? So if we consider the option D, the domain is 0 1, codomain is 0 1. If x equal to this, then is it true that f must have a fixed point? Can you create some counter example, that is some function which has no fixed point?
Sir, we can take f of 0 is equal to 1 and f of 1 is equal to 0.
Exactly. So define f of 0 equal to 1, f of 1 equal to 0. So it is continuous. Is it clear that this function is continuous? So if we define like this, then f is continuous. Because the left side or whatever side you choose, this is actually discrete topology. Because 0 is open set. This singleton set 0 is open in this open subset of this 0 comma 1. So whatever subset f inverse of, we need to see f inverse of u is open for every open set here. So f inverse of that set will be either some subset of this set, right? But here all those subsets are open, right? If you choose 0 comma 1, that will be a discrete topology, because 0, you can write 0, this singleton 0, uh, as something like this, minus 1 comma uh, 1.5 union 0, right? So a subset is open means, how do you see something is open in this relative topology? It should be some open set intersection this set 0 comma 1. Okay, so this is the way we check if something is open or not in the subspace topology. This is a subspace of real number. So you are correct that D is not correct, because uh, though f is continuous, but f may not have a fixed point. Okay, there is no x for which fx equal to x. Whatever x you choose, here fx is not same as x. So D is false. Now what about the other options? Can you construct a function for which fx not equal to x if the domain is open 0 comma 1? So for D this is okay. For B, can you create a function? So consider this function f maps 0 1 to 0 1. Okay, if we choose x equal to 0 1, consider this function defined by fx equal to x square. Okay, then can you see that if we this function has no fixed point, this is continuous, it is clear. It has no fixed point, is it clear? So let us see what happens. So if there exists some x0 belongs to 0 1, such that, so if we assume it has some fixed point, then we are getting x0 square is same as x0. But this equation will imply x0 into x0 minus 1 is 0. That is same as x0 is 0 or x0 equal to 1. So, but you can see the domain does not contain 0 1. Okay, so it is a contradiction. Therefore f has no fixed point. So this is also false. We have successfully created a function which has no fixed point. So this will look like this, uh, 0 comma 1. So the only fixed point means the point which lies on this graph. This is actually y equal to x. This graph, that is fx equal to x. Okay, so the points uh, which for which fixed point arises means that graph should intersect this line, right? Because fx equal to x, that happens if those points belongs to this line. But you can see geometrically that y that is fx equal to x square, for this graph the fixed point will arises at this 0 at x equal to 1 or x equal to 0. So it cannot intersect this line y equal to x. Okay, this is another way to see that this function has no fixed point. Now can you construct a counter example for option C? That close 0 comma open 1, this has no fixed point. Okay, let us create. So if close 0 1 to close 0. So let us again consider the problem graphically. So we want to construct a function whose graph will not cross this y equal to x, this straight line. can you create a function from this closed 0, that is the domain will be this closed 0 to open 1. This is the domain. So can you construct a function for which this will be true? That this function does not uh,
Sir, can we think about log x or not?
log x will be undefined because 0 is already there, right? You can say
Okay, sir.
yes. So you need to see a different counter example because range also should belongs to this closed 0 open 1, right? That is range will also belongs to this the height of the function, that is this function will be there. Okay, can you graphically imagine a function which does not cross this closed 0 open 1? uh, okay, let us, so if we consider this function x by 2, x by 2, fx equal to x by 2, this has only one fixed point which is 0. Now uh, we want something which has fixed point here. We'll create a function which has a fixed point here, that is this. This will be the only fixed point, so something like this. Can you imagine this function? At 0 the value will be half, at 1 the value will be 1. Can you write the equation of the straight line? That is at 0 fx, that is f of 0 will be half and f of 1 equal to 1. Can you write the equation of the straight line? That is graphically I am creating a function like this. So it start at half and it intersect at this point, but this point is not in the domain. 1 does not belongs to the domain. So at 1 this value will be 1. So this point is this function is nothing but define fx equal to half plus that is 1 plus x by 2, right? So again this function has, this is continuous function without a fixed point, right? If we try to solve, what will be the problem? So again, if there exists some x0 belongs to 0, this close 0 open 1, such that fx0 equal to x0, then we'll end up into a problem, that is 1 plus x0 by 2 equal to x0, so x0 equal to 1. But this is not possible because 1 does not belong to this interval, 1 is already excluded. So this is a contradiction. So C is also not true. There are some function. So this x equal to close 0 open 1, that does not mean that f has a fixed point. So now can we prove that uh, can we prove or disprove for this close 0 1? F must have a fixed point. So it says, let us try to solve option. F is a map from close 0 1 to close 0 1, a continuous map. Then can we prove or disprove that f has a fixed point? So let us see what happens. So let define a new function g from this close 0 1 to close 0 1. Define by gx equal to fx minus x. Sorry, uh, this is not close 0 1 to close 0 1. This is some close 0 1 to r. Okay, define by this rule gx equal to fx minus x. So there are several cases, right? It is possible that g0 equal to 0. If this happens, then 0 is the fixed point, right? So case 1, if g0 equal to 0, then 0 is the fixed point. That is g0 equal to 0, that means f0 minus 0 equal to 0. f0 equal to 0. So 0 is the fixed point. Not the, is a fixed point. Now case 2. Assume another case. If we assume g1 equal to 1, again we are the same conclusion will hold, right? Sorry, uh, yes, g1 equal to 1, that will imply that f1 minus 1 equal to 1. Sorry, g g0 equal to 0 is okay, g1 equal to 0. If we assume g1 equal to 0, then we will get f1 minus 1 equal to 0, then f1 equal to 1. So in this case, 1 is the fixed point. 1 is a fixed point for the function f. Now case 3. Suppose none of this is true. That is, uh, g0 is non-zero, g1 is non-zero. Case 3 is g0 is non-zero and g1 is non-zero. So there will be 3 cases, right? Either g0 equal to 0, then we are done. g1 equal to 0, we are done. Now the remaining case is none of these are true. g0 is non-zero and also g1 is non-zero. Those two are not true. Then what will happen? So then g0 means g0 is defined by f0 minus fx minus x, right? X means 0. So f is a function from close 0 1 to close 0 1. So this is non-zero. This belongs to close 0 1, but this is non-zero. Therefore, g0 is positive because g0 belongs to close 0 1, but it is also given that g0 is non-zero. Therefore, g0 is positive. Now g1 is non-zero. That means again g1 means f1 minus 1. This belongs to 0 1. Sorry, sorry, extremely sorry. The range of f is 0 1, right? Range of f, this is actually 0 1, not 0 1, but it is contained in 0 1. So if you subtract 1, so that means range of f. So we know by definition it is given that fx is in between 0 and 1. Then if we subtract 1, then this will be like this, right? Therefore, G1 means G1 belongs to this. The range will be contained in this -1, 0, this closed interval. Is it clear? But we also assume G1 is non-zero. Therefore, since G1 is non-zero, therefore G1 cannot be zero, therefore G1 is strictly negative. So here the same reasoning, for the same reasoning. F0 belongs to, because range belongs to close 0, 1, but we have already assumed that G0 is non-zero, that is F0 is non-zero, therefore F0 is strictly greater than 0. G0 is strictly greater than 0. Is it clear? F0 will lies in between 0, 1. So can you now use intermediate value property? So what is the statement of intermediate value property? If x is connected, f is a map from x to real number, x is connected, this is continuous map, a continuous map from a connected space to R. So, and R belongs to, so R is something in between Fa and Fb, then there exists some x0 such that f of x0 equal to R. This is intermediate value property, right? IVP. So note that 0 is strictly less than 0, strictly greater than 0, and G1, this is strictly less than 0. So 0 is in between those two things, right? So therefore we are getting this property. So IPP intermediate value property says there exists some x0. So there exists some x0 belongs to the domain. Domain means R. So sorry, domain means this closed 0, 1, such that g of x0 will be that intermediate value. Okay, g takes all the intermediate value between this any two points in the range. So gx0 equal to x0. Sorry, gx0 equal to this intermediate value 0. But by our construction, g is same as fx minus x. Therefore, f of x0 minus x0 equal to 0. Is it clear? F of x0 equal to x0. So only correct option is option A. Intermediate value properties will guarantee there exists some fixed point, or this, if we consider this closed 0, 1. So closed 0, 1 means this kind of range. The domain, and this is the domain cross range. Domain cross codomain. Close 0, 1 close 0. So whatever continuous function you choose, in between this close 0, 1 close 0, 1, this must intersect. This cannot be entirely lies under or above this y equal to x. This is not possible. It should be clear from the graph that whatever function you choose, it must cross y equal to x. Okay. Which of the following subsets are connected? So we are considering M2R. M2R means all 2 by 2 matrices. So again, the topology is usual topology. M2R means all 2 by 2 matrices. A, B, C, D, where all A, B, C, D belongs to real number. Okay, any 2 by 2 matrix belongs to M2R. Now, can you see this set is connected or not? So, note that this is actually homeomorphic to R4, real number. So, here the usual topology is given. On the right hand side, the usual topology is considered. Okay. Therefore, uh, so this is a continuous map. This is actually a homeomorphism. So send this entry ABCD. This will map to this pair tuples ABCD. Okay. Define this homeomorphism f of ABCD equal to this ABCD. So this is continuous. So on in for M2R, you can define metric D between two matrix A B. Suppose A is this metric, this matrix, and B is another A dash B dash C dash D dash. Then you can define the distance by square root of sum of the entry square Aij square minus Bij square. Okay, so here I am considering A11, A12 like this entries. So if we consider two matrices, two different matrix, then you can define the distance between those two matrices by this formula, same equation. So it should be clear that this map is nothing but this representation is nothing but rewriting same R4 in a different manner. Okay, so this is actually a homeomorphism because we are dealing with the same metric, just a different representation, different notation. And the interesting thing is that you can define several different metric or distance between A and B. For example, one distance will be like this: take sum of Aij minus Bij. You can also define by this method. So there are lots of different distances, but all those uh, distances gives the same topology. Okay, it is like choosing a different basis. For example, recall that for R2 we can choose bases like this kind of disk, but we can also choose basis like this, some kind of square. So those different metric, those will correspond to those different open unit disks. Okay, this is an interesting exercise you should do on your own. Okay, so the conclusion is that M2R is nothing but this R4. But as we know that R4 is connected. Why? Because of the fact product of connected sets is connected. Take any arbitrary product or any finitely many product of connected set, you will again get a connected set. Okay, R is connected, therefore R4 is nothing but product of R 4 many times, right? So this is connected. And connectedness is preserved under homeomorphism. So M2R is connected. Now what about A belongs to M2R such that trace of A equal to 0? Is it connected? Option B. So A is connected because product of connected set which is connected. So we are using some facts. Product Fact 1, product of connected sets is connected. And fact 2, it is also easy to see homeomorphism preserve connected components or connectedness. Homeomorphism is preserved under connectedness. It comes from the property that image of a connected set is connected under a continuous map. So homeomorphism means there is also a continuous function in the reverse direction. So this is image of this thing. So this connected will imply this will connected, and similarly, if we assume this is a connected, then the inverse map will imply that domain will be connected. Okay, that's why if and only homeomorphism preserve connectedness. If once x and y are homeomorphic, x is connected will imply y is connected, and vice versa. Okay. Now consider a all such 2 by 2 matrix such that trace of a equal to 0. Now what about this? Is it connected or not? So let me denote it by some S, a set S. So S contain consider this map F from S to R3. You should be familiar with this example. What is the dimension of this space? As a vector space, what will be the dimension of this space? So there are 4 entries: 1 1, a 1 2, a 2 1, a 2 2. But the condition is sum of the diagonal is 0. Sum of the diagonal, yes, exactly 3. Sum of the diagonal is 0 means one of a11 or a22, one of this is dependent. Okay. So exactly the same example will work. So send a11, a12, a21, a22 to a11, comma a12 and a21. So I am removing a22 because a22 is dependent. Okay. So the fact is that this is a homeomorphism. Why? Can you write the inverse map? For example, so this is continuous. It should be again clear. Now, can you write G in the reverse direction R3 to S? What is the map in the reverse direction? Okay. So take any point A, B, C. Okay. We want to create a matrix. So it will be like the opposite way. So first entry should be mapped into the first place, 1 1 place. Second entry will be mapped to 1 2th place. So A will be here, 1 1 place. B will be mapped here, 1 2th place. Now what will be see where this A21 goes? It goes to 2 1th entry, right? So C maps here. Now what will be this value of this 2 comma 2th entry? So note that trace of the matrix is 0, right? So the entry will be minus A, right? ABC comma minus A. So this is also continuous map. And interesting thing is that G compose F is identity and F compose G is also identity. Those two are identity. You can check that those two will be satisfied, because this is, let us check this property. So choose a point ABC, it goes to ABC comma minus A. Now ABC comma minus A will send to ABC, and the last point will be nothing, that is A comma B comma C. So I am getting an identity map. First start with G and then apply A, that is same as identity map. Okay, and similarly if we start with F, again apply G, we will get identity. Check those two things, very easy. Therefore F is a homeomorphism. So again, homeomorphism preserve connectedness. R3, since R3 is connected, this will imply S is connected. Okay, same homeomorphism will give the answer. So those two sets are connected. What about GL2R, general linear group? Is it connected or not? What is the answer? Okay, let us see. Consider this function f from this GL2R to real number. F of f evaluated on a matrix A is defined by determinant of A. So this is continuous function. Again, determinant of A is nothing but a polynomial of its entries. Therefore, it is continuous. This function is continuous. Every polynomial is a continuous function. Now, can you see that? Now, what is the conclusion? What is the range of this? What is the determinant of a function of a matrix? Matrix GL2R means determinant is non-zero. Exactly. So range of, what will be the range of f? So range of f is everything other than 0, right? It is onto this, sorry, GL2R to R minus 0, that will be onto. Okay, because for any point A other than 0, you can always choose a function like this. Uh, you can choose A times identity, that will work, right? For any point A which is non-zero, it always has a P image, A times identity. So range of f is R minus 0, but note that R minus 0 can be written as disjoint union of two open sets. Okay, R minus 0 means this union this. We are removing this origin. Okay, So range of F is disconnected. R minus 0 is disconnected. It can be written as disjoint union of two open sets. Now what is the conclusion? So again, recall the property that image of a connected set under a continuous map is connected. Image or range, whatever we say. Okay. So if we assume, therefore it should be clear, right? Therefore GL2R is not connected. Contrapositive statement, right? So F map X to Y, if X connected imply F of X connected. So F of X not connected, F of X is disconnected imply X is disconnected. Is it clear? The contrapositive statement. So F of GL2R is disconnected. Therefore X must be disconnected. Now what about O2R? So this is disconnected. C is not true. Now what about O2R? O2R means orthogonal group. Can you tell me the answer? Is it connected? O2R is connected or not? Okay. So O2R again consider the same function. Okay, f of a equal to determinant of a. Then what will be the range of orthogonal group? Orthogonal group is determined by this property. A transpose is identity. Right? This is the property which shared by orthogonal groups. Yes, modulus is 1. But we are considering real orthogonal group. Then determinant of A will be either, so determinant of A times determinant of A transpose is determinant of I, which is 1. But this means determinant A whole square is 1. That is determinant of A is plus minus 1. And moreover, take any, for example, plus 1 has a pre-image. Identity, determinant of identity, this is orthogonal group, this is plus 1. Determinant of minus identity is minus 1. Right? So range of this function f is precisely plus minus 1. There will be 2 points, plus 1 and minus 1. But again, this is disconnected, right? Plus minus 1 as a subspace of R, this is disconnected. Is it clear that plus 1 and minus 1, these 2 points are disconnected? Because if we consider, if we say this is A or this is some set, probably something like T, then T can be written as T union, sorry, T can be written as minus infinity comma 0 union T intersection minus 0 comma infinity. So this union T intersection 0 comma infinity. this is nothing but minus 1. This is actually plus 1. So T can be written as disjoint union of two open set. So in subspace topology, this is open. In the subspace T, this is open. In the subspace T, this is also open. Open intersection thus set T, right? Therefore, T can be written as disjoint union of two open sets. Hence the conclusion. Therefore, by the same analogy, range become disconnected. That means domain cannot be connected. Range is disconnected. That will imply the domain must be disconnected. Okay, this is the main the property we are using. O2R. This is range is disconnected. Therefore, O2R is disconnected. So D is also not true. The subsets of R which are homeomorphic to 0, 1. Can you see which of the following are homeomorphic to 0, 1? So can you see that 0, 1 is homeomorphic to AB? 0, 1 is homeomorphic to AB. This is nothing but stretching and shifting. That is some scalar multiplication and shift by some scalar constant. So the function, the homeomorphism f of x equal to uh, a plus bx. Note that at 0 the value will be a, at 1 the value will be b. Okay. So this is homeomorphism. You can write the inverse map. Now what about a comma infinity? Can you see that 0 comma 1 is also homeomorphic to a comma infinity? So define fx equal to 1 by x. So if we define fx equal to 1 by x, then the range is at value 1 the value will be 1, at value at 0 it will becomes infinity. So the curve will be like this. The domain is 0, 1, so it will be like this. Now we want to start from a, right? So sorry, something like this. So it start from 1 and it will get to infinity. But we demand it should start from a. So shift it by a, add a plus 1 by x, sorry, a minus 1 plus a minus 1. Okay, just shift it by a minus 1. So if we want to start from a, uh, then at x equal to 1, the value should be 1 plus a minus 1, which is a. Is it clear? Okay. This is homeomorphism, you can check. How can you see that this is homeomorphism? Y equal to this 1 by x plus a minus 1, then x equal to y minus a plus 1, 1 by. Okay, there will be some problem. No, it is okay. A to infinity. So it is okay. It is okay. So this is homeomorphism. I was checking the domain and range. So the reverse direction, the reverse map will be given by this equation. So G of x or G of y equal to 1 by y minus a plus 1. Okay, this is the inverse map. Similarly, you can check that this is also homeomorphism. Just change the sign 1 by x, instead of 1 by x, replace it with minus 1 by x. And r, this is also homeomorphic. 0 comma 1 is homeomorphic with r. You can also prove that. Similar kind of map you can use. Now, other than those intervals, is it possible any other subset which is homeomorphic to open 0 1? Is there exist any set which does not belongs to this collection, but that is homeomorphic to open 0 1? So the answer is no. Why? Because we know the property. Any connected subset of R is an interval. Okay, so interval means there are lots of choices. It will be of this form AB, or one side is A, one side is B, and moreover AB is allowed to take the value infinity. A comma B can take plus minus infinity. Okay, so those are the shapes of any kind of interval. There is also another trivial choice, singleton A. Any connected subset of R is interval. So connected means uh, connected non-trivial subset, because empty is also, empty can be written as interval, because empty can be written as a comma a, open interval a comma a. So those are the only possibilities. There is another interval, another type is closed a closed v. But among these, only this is allowed. This and another choice is real number R. Other than this, all those are non-homeomorphic. Empty cannot be homeomorphic with AB, not even a bijection. Open AB has infinitely many elements, but empty means there is nothing. Similarly, this is not possible. Those are not even a bijection. These two are not possible. And open AB, that cannot be homeomorphic with one side closed. Why? Because you can see that if one side is closed interval, then if we remove a point A, just remove the point A. If we remove the point A from this interval, this will become A comma B, which is connected. But removing any point from this interval, this becomes disconnected. But we know homeomorphism always preserve connectedness, right? That's why this cannot be homeomorphic with this point, this interval. Similarly, those two are not homeomorphic. This is one possible choice. This is another possible choice, and AB are allowed to take the value infinity, plus minus infinity. Okay, there is another question. I am giving hint for this question. You should try. Consider gx equal to fx minus f of minus x and use intermediate value property. Another question you should try, that uh, in with discrete topology, this is homeomorphic with n with sorry, q with discrete topology, but n with usual topology. Usual means as a subspace of real number is not homeomorphic to q with usual topology. This is another interesting question you should try. Up to this, is there any doubt? So this is true false question. This is actually true. Answer is true. डिक्शनरी टोपोलॉजी क्या होता है? Okay, dictionary topology means it is actually an ordered topology. So, for example, on R2 you can give a dictionary topology. So in R2 there is some ordering, right? Any point in R2, any point in R, choose any 2 point A less than B. Any 2 point, one is A, another is B. There is an ordering. But in R2, it seems there is no natural ordering. But this is not true, because you can always think this kind of grids. Can you see the grids? So for finite grids, let me draw this. So you can, for finite case, it is easy to see that you can always give ordering like this. So this one, this point is bigger than this. So on the right hand side, it gets bigger. Then, sorry, this. Then from here we start this. After that, the ordering will, so the those are getting bigger and bigger. So I want to say that if we choose those 2 points, one point is this, another point is this, then the right one is bigger. Okay, the more we go in the right direction, it becomes bigger and bigger. And now, if we consider another point on the above, then this should be also big. Now, what about this point and this point? Can you compare? So yes, we can compare. We'll define this point is bigger than this point. Okay, so the ordering is like this. So the point on the in the right direction is bigger, but if it starts in the second grid, it is automatically bigger. So I want to mean, so to compare those 2 points, xy, x1 y1 and x2 y2. So I will define x1 y1 is less equal to x2 y2 if, if y2 is greater equal to y1, then we always assume if this y2 is greater equal to y1, then that will be bigger than x1 y1. But there is another case, y2 can be same as sorry, y2 is greater than y1, then uh, it is strictly bigger. So let me define the order like this. Now there is another possibility, y2 equal to y1. Okay, then there are two possibilities, right? Either x1 less than x2. So those two are distinct point, mean one of the component must be different. So if y2 is greater than y1, then the second one is bigger. Now if y2 and y1 are same, then if x1 is less than x2, then that again second one will be bigger. Okay, I can define the ordering like in this way. First start with this, then this one is bigger. If y2 is bigger, then we'll that will be always bigger. For example, this point is bigger than this point or this point, whatever, something in the lower grid. Okay, and if 2 points belongs to the same height, then the point which belongs to the rightmost, that is bigger. So this is how we can give ordering. And now if there is some ordering, we can define a topology similar to the real number, right? In real number, we always can define a topology, some open interval. Here the similar kind of thing will happen. So again, here the topology is defined by this kind of interval x comma y. So this is, for example, this is z and this is w. Suppose this is z, this is w. Then we define the interval by this z comma w, this kind of open interval. Because there is some ordering, we can always talk about this kind of interval, right? T belongs to zw means t is strictly less than w, t is strictly greater than z. So define a topology whose basis is given by this interval, open interval. Z and W belongs to the space X. Okay, so this topology will be called dictionary ordered topology. It is similar to dictionary, right? In dictionary, what happens? If those, so maybe I have done in a reverse thing, that is in dictionary uh, the opposite. So okay, um, it is the opposite ordering is used. So if X, for example, consider these two letters, apple and ball. So which is bigger? Which will be uh, in the end and which will be in the beginning? So apple will appear in the first pages, right? And ball will be in the remaining pages. So ball is bigger than apple. Yes, exactly. Similarly, now suppose both start with A. For example, apple and uh, something like arrow. Now which will be bigger? So both has the same entry, but now we'll see the remaining entries. Okay, so there is P and there is R. Exactly, arrow is bigger. So this is how the dictionary here the topology is defined. Okay. Similarly, you can define for Rn also the same similar generalization. Instead of, so here um, we are considering 2 points, but now we can consider n many points, x1, x2 up to xn, and y1, y2 up to yn. We can compare those tuples. So that topology is different, right? Here the open sets are like this, then after this like this. Those are some open sets like this. So this is very strange topology. Uh, is it clear? I have written in opposite way, but you can define another way also. Maybe you can define this one is bigger. You can change the conditions. So you need to create some order, and now you can, since there is some ordering, then you can always talk about some interval, because interval means anything which lies between this A and B. So ordering is given, then you can generalize the interval in real number, and now just define the basis as those intervals. And intervals will form a topology. AB belongs to that space R. Okay, and that space maybe R2. AB. Is it clear that generate the topology by this basis where Z, W belongs to some Rn. Z, W both are element of Rn. So here I was giving an example for dictionary topology on R2, but you can generalize this fact for Rn. So here for Rn there will be more condition. First, if so maybe the better way will be like the other one. First, try with x1 and x2. If x1 is less than x2, then we define this equality. Now if x1 equal to x2, then we'll check y1 and y2, compare y1 and y2. So is it okay, Kamalji? Is there any other questions? If not, okay. If not, then let us stop here. Is there any question, Isika and Dipan? Okay. Okay then. Thank you for joining. Let's stop here. Thank you. And happy Teachers Day to all of you. Let us stop.